AI agents need to process continuous streams of information, but context windows impose strict physical limits on this capacity. When a model must hold too much historical data, it hits a computational ceiling where it violently fractures and cannot process further inputs. Pushing the limits of these windows carries steep financial penalties. Every token processed incurs an API charge from providers. Maintaining a massive rolling context for an enterprise-level agent causes operating costs to compound constantly. There is also a performance penalty. When a language model searches through a sprawling context window, it often suffers from the lost-in-the-middle effect, ignoring vital evidence buried in the center. Researchers from Huawei and the Chinese University of Hong Kong partnered to engineer a structural alternative to expanding context windows. Their research proves that continually paying for larger context windows is mathematically unsustainable for long-term deployment. Building a permanent, reliable AI agent requires a different approach to memory entirely. To understand their solution, we have to look at the current industry standard for agent memory, known as eager memory consolidation. This is the architecture driving systems like MEM0 and AMEM. Eager systems have a costly flaw. They invoke an expensive language model to extract facts from every single message. Send 10 casual messages, the model fires 10 times. The cost scales directly with input volume, wasting power on transient noise. The Huawei and CUHK team looked to human cognitive science for an alternative. Humans do not permanently store every passing detail. We consolidate short-term experiences into long-term memory only when we observe recurring patterns. This chart shows the token consumption for memory construction. By engineering a system that waits for recurrence before extracting facts, their architecture drops memory construction token costs to $193,000, an 87% decrease compared to eager models. True infinite memory requires treating compute as a scarce resource. An agent scales effectively when the system is designed to evaluate data selectively rather than processing every input by default. This selective evaluation is driven by a new 3-tier architecture called RecMem. It starts by handling raw data at the bottom layer, subconscious memory. When a user and an assistant exchange messages, RecMem groups them into a single atomic unit. Instead of sending this to a large language model, RecMem runs it through a cheap, lightweight encoder to produce a dense numerical vector array. If a user asks the agent for a birthday cake recommendation, that entire exchange, turn 1, is mapped mathematically and filed into a vector database. Throughout this ingestion process, the primary, expensive large language model is not invoked. It remains completely asleep. Translating raw text into cheap vectors builds an exhaustive, highly searchable historical record for pennies on the dollar. Of course, the agent eventually needs to form long-term memories. The system relies on a mathematical gating mechanism to decide exactly when the main LLM should wake up. Every time a new message enters the subconscious tier, RecMem runs a fast cosine similarity search across all previously stored vectors. To trigger memory consolidation, the incoming message must clear 2 strict thresholds. It must be semantically similar to past messages, and it must push the total count of related messages past a specific limit. If our user returns later and makes a casual comment about the weather, this turn 2 registers a low similarity score against the earlier cake discussion. The LLM remains asleep. But if the user logs in for turn 3 and mentions their sister has a peanut allergy while discussing the cake order, the math changes. The message clears the similarity threshold, hits the required count limit, and immediately wakes the LLM. By linking compute strictly to mathematical thresholds, the system filters out daily noise and reserves its processing power for patterns that actually matter. Once the LLM wakes up, RecMem activates Tier 2, episodic memory. The system pulls the entire cluster of related cake messages up from the subconscious layer. The model takes these chronologically sorted raw interactions and synthesizes them into a single high-level narrative. It condenses the back-and-forth dialogue into a coherent event summary. To keep this storage tier compact over long periods of time, RecMem employs a merge-first strategy. Rather than generating a brand new episode every time a topic recurs, the system updates the existing episode in place. This prevents an evolving topic from fragmenting into disconnected timeline entries. Through episodic memory, the agent maintains a clean, chronological understanding of user intents, avoiding the data bloat that slows down retrieval. Summarizing conversations creates a structural problem. When an LLM compresses dialogue into a narrative, it inevitably discards fine-grained details. To prevent data loss, RecMem activates its highest architectural layer, Tier 3, semantic refinement. A secondary LLM pass acts as a targeted extractor. It scans the raw subconscious cluster for highly specific atomic facts, like the name Mia or a peanut allergy, that the narrative summary missed. These extracted facts are stored independently of the timeline. Because they exist as isolated nodes, the agent can retrieve them precisely without having to parse an entire episodic summary. Semantic refinement operates as a high-resolution safety net. It guarantees the agent will never forget a hard user constraint, even if that constraint is buried inside a long, casual conversation. This three-tier structure determines how the system constructs memory, but its actual utility is tested during the retrieval phase, when the user asks a complex question. To formulate an answer, RecMem pulls a strictly budgeted mix of contexts from all three tiers simultaneously, balancing raw interactions, chronological summaries, and specific facts. Researchers tested this retrieval capability against a rigorous benchmark called LongMemEval-S, designed to evaluate agents handling dense, task-oriented interactions over long periods. The results show RecMem outperforming eager consolidation models across the board, with its most dominant victory occurring in temporal reasoning. The reason comes down to sequence. Eager systems summarize every turn immediately, fragmenting an evolving timeline. RecMem delays clustering until a topic is established, preserving the true chronological order of interactions. By engineering patience into the architecture, the system gains a superior, more accurate understanding of how events actually unfold over time. In software engineering, there is always pressure to reduce costs further. This prompts a critical question. What happens if developers strip out a memory tier to save compute? This bar chart shows an ablation study. Removing the subconscious tier causes a catastrophic failure, plummeting accuracy from 81 down to 51%. Eliminating the semantic tier yields a similar failure, driving accuracy down to 70%. The layers are functionally interdependent. Artificial intelligence scales effectively when it mimics the efficiency of human cognition. Real intelligence requires knowing exactly when to ignore useless data. Building long-running LLM agents requires looking past the raw size of a context window. Sustainable performance comes from evaluating data selectively.